Tales to tell? No? I don't know. I was just talking to a professor friend of mine. He always starts with, so who's got a story for us today? You could chat about your boyfriends. I don't know. I don't want to know about your boyfriends. You can tell me about your boyfriend if you want. I don't have any cute stories to tell, I suppose. Let's talk about sequences a little bit more. So yes? You got a cute story? No.
What's going to be on the quiz?
Oh, yes, I did mean to mention, thank you for reminding me. Unfortunately, I forgot to bring my little thing about old questions, but I'll have to send an email about that. But the quiz, I would like to, as I mentioned last time, the questions on the homework for this week about sequences are kind of easy, and I want to eventually have more involved questions about sequences. So for the quiz this week, it'll be just arc length. And I know some of you already got the arc length question on the test, and so those of you can just sit back and feel superior to everybody else while they're doing the arc length question again. So it's going to be just arc length, and then as usual, everybody can choose an old one. And we had the midterm, but it's not like those old ones are gone forever now. You can still retry to do the old ones from before the midterm. Right? Does that answer your question? Yeah. So arc length question plus an old one. If you already got the arc length question, you don't have to do that one. But I'll hand it out to everybody. All right. And I will send an email this afternoon asking you to reply and tell me which old one you want. Sorry, I forgot to bring my little list. Okay, great. I had just one last thing to say about sequences, and then we're going to move on to talk about series. So one last thing to say about sequences. At the end last time, we discussed what it means for a sequence to be bounded above and also bounded below. So bounded above looks like there is some upper bound, up here, which the book writes with a big M, and it just means the points always stay below that line, right? It does not necessarily mean that the points increase asymptotically towards the line. It just means they always stay above that line. So this is bounded above. And then bounded below is similar, but with a lower bound. So that means there's some kind of bottom number, which our book writes as little m, where the dots always stay above, right? This is bounded below. And neither of these things means that it converges, right? Like here, I wasn't being very, very specific about it, but it looks to me like maybe these points are going to oscillate forever. So even though they're bounded, actually this one is both bounded above and below, because I could put a line up here and also a line down here. Even though it's bounded above and below, it does not mean that it converges, right? That's what I was saying at the very end last time. There is a relationship between convergence. It just goes the other way around. I think, would you agree, what if I start off with a sequence that converges? So if we already know it converges, so the picture for a sequence which actually converges, that means as you go out to the right, it actually does approach some specific value, right? So I'm trying to make this sequence approach here. These red dots are all approaching the same value as you go off to the right. I think that means automatically that it is bounded above, right? You can actually draw a horizontal line above all of them. Certainly it's true for this picture, but actually in any sequence that converges, there is always an upper bound for all of them. You might worry about something like, if we know it converges, actually, if you already know it converges, there must be an upper bound. That's because if it converges, it means as you go out to the right, these points do not go up forever. They can only go up so high, but then they have to level off at some point. Yeah?
Can it converge but only have a lower bound?
No. So I'm also going to say, yeah, whatever I'm saying here, exactly the same is true of lower bounds. So if it converges, there must be an upper bound, and similarly, there must also be a lower bound, right? Down here. If it converges, you know that there has to be bounds like that, because since it converges, it means as this sequence goes out to the right, it doesn't go up forever, and it also doesn't go down forever. And so it has to eventually be in between this sort of bracket given by the two bounds. I said eventually. What about before? I said as you go all the way to the right, then it does have to eventually end up in between the two lines. But what about before that? Can anybody say? How do we know that it doesn't like go up to infinity right here and then come back down and eventually stay inside the zone here? Like that actually is possible of a function. You know, you can have a function which, say, goes up to infinity and then comes back eventually. Can we say, is that possible for a sequence? And I just insert here and a lower bound. A lower bound. Is it possible for a sequence to go up to infinity and then come back down? The answer is no, because a sequence is just individual dots. Individual dots cannot go up to infinity and then come back. A continuous line can, well, not continuous, but a line can go up to infinity and then come back, you know, like this, right, with a vertical asymptote. A sequence cannot approach a vertical asymptote because it only has, you know, 2 or 3 dots right there. It can't go up forever arbitrarily close to the asymptote because it's just isolated points. They don't get close to an asymptote like this. So this kind of a situation does not occur with sequences. This is a little strange, but it's a major difference between sequences and continuous functions or real valued functions, all right? If it converges, there must be an upper bound and a lower bound, and it cannot go up to infinity somewhere in the middle and then come back down from infinity. It can only go up so high before coming back, all right? There must be an upper bound and a lower bound if it converges. What about the other way around? If you know there's an upper bound and a lower bound, this does not mean that it converges. So I'm gonna actually, what I wrote there, I'm gonna write this as a theorem. It says if lim n goes to infinity, a n exists. That is to say, if it converges, that's the same way of, it's another way of saying it converges, then a n is bounded above and below. All right? If it converges, then it automatically must be bounded. And I would also like to talk about the other way around. If it's bounded above and below, does that mean that the sequence converges? The answer is no. We talked about that last time. This is what we refer to, what we call the converse. It's fancy terminology that you will learn a lot more about when you take discrete math, if you take discrete math. The converse would say the other way around. If it's bounded above and below, then it converges. This is actually not true. I'll put this sort of in quotes because this is false. And an example I mentioned last time, something like, you know, minus 1 to the n. This is bounded above and below, but it doesn't converge. Right? So this one is bounded, but doesn't converge. All right? So there is no such theorem that says if it's bounded above and below, then it converges. There is something that is kind of like the next best thing, and we have to talk about it because it has a big, important sounding name. This is called the monotone convergence theorem. It says that stuff that I was saying there before actually is true if the sequence is monotone. So if an is monotone, remember monotone, the word monotone means either increasing or decreasing. If an is monotone and bounded above and below, then it converges. All right, and I'll try and draw a picture to convince you. I think you will be immediately convinced that this must be true if you think about a picture. If an is monotone and bounded above and below. So I'm going to draw a sequence which is bounded above and below. So here's let's say here's the upper bound, here's the lower bound. So when I draw the sequences, the dots, they have to stay in between those two bars inside this horizontal strip. And I'm also going to draw it to be monotone. Remember, monotone means either increasing or decreasing. So maybe if I put the first dot here, and let's draw this to be increasing, all right? It means the next dot has to be a little bit higher up. The next dot has to be a little bit higher up. Higher up, higher up. Anybody agree with me that this must converge to some value? It has to go a little bit higher every time. It can never go lower, so that means it cannot oscillate. It can only go up on this picture. And there's only so far you can go, right? You're not allowed to go above this line. If you keep on going up every time but never above this line, then it has to stop going up eventually, right? It has to level out to some particular value. You could say one way that could happen is if it actually just straight up increases to approach M. It could converge to the line up top, but it could also converge to some line lower down. That's also a possibility. All right, but here, if it's increasing, and bounded, it must converge. That's what this picture is meant to convey. This is not a proof of the monotone convergence theorem. If you want that, you should take our course called Real Analysis if you're a math major. It's a fairly hardcore course, but if the sequence is increasing and bounded, it must be converge. It must converge. Converge, I wrote. I meant converge. Converge. All right? And the same is true for decreasing. So this one being increasing converges to this top bound, or it might converge to something lower down. I mean, my picture didn't, but you could draw it increasing and converging somewhere else. And similarly, if it was decreasing, then you would expect it to converge to the lower bound or to some other value down there. So if it's increasing and bounded, it must converge. And also, if it's decreasing and bounded, it must converge. And that's why the whole theorem says if it's monotone, which means increasing or decreasing, and bounded, then it must converge. All right, this is called the monotone convergence theorem. And it's one of the big theorems from the theory of real number sequences. All right. Any thoughts about that? The monotone convergence theorem. It's a classic. An oldie but goodie, as they say. All right. And this is all I wanted to say about sequences. So I think we can move on then to series. We will have some more homework problems for next week about sequences. Things about show that the sequence is increasing or decreasing, which we did in class last time, but we're not on the homework for today, where you end with shoon. All right? It's not necessary to write that if it makes you feel stupid. Nothing makes me feel stupid. All right, let's talk about series. So sequences means numbers in a list one after another. A1, A2, A3. Series is when you try to add together all the terms in a sequence. So a series is an infinite sum, which is a little weird just from the get-go, but it means you try to add up all the terms of all the terms in a sequence. Right? So when we have a sequence AN, this is a sequence. The corresponding series is written this way: sum of AN, n equals 1 to infinity. All right, this is the corresponding series. So every sequence has a series, and the sequence itself might converge or diverge, and also the series might converge or diverge, but these are different ideas. If I ask about if the sequence is converging, means these individual numbers, each one, do they approach a certain limit? Whereas this means if I am trying to add them all up, does that actually approach a limit? Or do I just like get infinity if I try to add them all up? Or something else, all right? So this is the difference. Some people confuse the two terms, but this is what a series is. A series is adding them up. A sequence is just those numbers by themselves already. All right? And I suppose the first sort of non-obvious thing is that actually sometimes you can add together infinitely many things and have it add up to just a finite number, right? When you add together infinitely many things, it doesn't always just sort of equal infinity. And the nice example that we've already seen before, for example, we saw already this, the sum n equals 1 to infinity of 1 over 2 to the n. This actually adds up to 1, because what this looks like is 1/2 plus 1/4 plus 1/8 plus 1/16. And if you think about these as areas, you can think of like the unit square, and this is a half. If I cut in half what remains, that would be a fourth. If I cut in half what remains, that would be an eighth. 1/16 would be this. That's about as small as I can draw. But you will see, by sort of stacking these up in this way, if you add these up, actually, even if you take sort of infinitely many of them, they never escape this little box here, right? Because every term that you're adding is just half of the remaining empty space. And so, we have to talk about this, but somehow in the limit, as you add together infinitely many of these, it actually adds up and fills up the whole the whole box, which is area 1, all right? But I hope that this is at least vaguely convincing that this series really does add up to 1. Even though there's infinitely many things that I'm adding together, they do not add up to infinity. They add up to a finite amount. And in this particular case, that number is 1. All right, so what I want to talk about today is just like, how can we calculate these answers? How can we calculate this? You know, in a typical example, you don't want to rely on being able to draw a cute little box here, right? This argument basically only works for this specific example. We want more general tools to be able to add up the value of a series like this. All right. I think as a preliminary, we should really talk about what does this infinity here even mean, right? Usually when we use infinity in calculus, that is somehow a stand-in for a limit of something or other, right? So the first kind of preliminary question would be, how do we make sense of that? So a more sophisticated way of asking about this is, what is the actual definition of sum n equals 1 to infinity an? It should surprise no one that the actual definition of that somehow involves the limit of something or other, the limit of something as something goes to infinity of something, 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 right? This is what we expect for this definition to say. Anybody seen this before? Anybody have an idea? What does it actually mean when I say add up infinitely many things? Yeah?
It's like the Riemann sum or something.
It is vaguely like a Riemann sum. Although a Riemann sum doesn't involve an infinity inside the summation.
Okay.
A Riemann sum usually has this format. Some stuff in here. And then this sum goes up to n. Well, the Riemann sum also is difficult to deal with, but as we all know. Any ideas? Yeah?
Is this the formula where you have like the n factorial on the bottom? Or that's
No. That's maybe the binomial theorem. Yeah, I'm not sure. There are factorials a lot off. That's trying to delete this. What could it mean to add together infinitely many of these things? An idea?
Interval?
An integral, this is not a bad idea because, yeah, when you add up infinitely many things, that's kind of what an integral means. Although I would say every integral can be expressed as a kind of series, but going the other way around, you don't typically start with a series and turn it into an integral, fortunately. Any other ideas? I would say what maybe this is inspired by my cute little picture here. In order to take this sum of infinitely many terms here, I sort of started off by, okay, well, if I only take one of them, it looks like a half. But if I take the first two, a half and a fourth, it looks like that much. If I take the first three, it looks like this much. So the idea in terms of expressing this as a limit, we build this using what we call the partial sums. And this is not an obvious idea if you, it's not easy to come up with this basic concept, but it's a very fancy way of thinking about this integral. The partial sums, I mean, you think about, okay, what if I just took the first one by itself? That's something. What if I added the first two? That's something. What if I add the first three? These are called the partial sums. They result from adding up only part of the series. So they are, the definition of the partial sums is, we're going to call them another, this is just another sequence. S1 is just A1. That's not very interesting. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. And so on. S4 would be the sum of the first four things. These are called the partial sums because, of course, the entire sum is is adding up infinitely many things. These are adding up only parts of it, only the first bit, right? So these are called the partial sums, and this is another sequence. This is a sequence, which I could write as Sn, right? And generally speaking, the definition of Sn is it's A1 plus A2 plus blah, 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 plus An, right? That's what Sn is, and this is the name of this. This is the nth partial sum. All right? And that, I put a dot, 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 but this is not infinitely many things. It's just n things, right? You go 1, 2, 3, 4, etc., until you get up to the top. So these guys individually are not infinite. They are finite sums. And then, if you want the entire infinite sum, you take the limit of this as n goes to infinity. That's the trick. And so the definition, then the definition of the series is the series, the sum n equals 1 to infinity, an, is defined to be the lim n goes to infinity of Sn. All right, sorry, that's a little ugly. This is how you make sense of a series adding up to infinity. You turn it into a sequence, and then you take the limit of that sequence. All right? And then I will just say, over here, you can, I mean, hopefully, sometimes it's really hard, but in theory, you can calculate this using tricks for limit of sequences, right? The right-hand side of that is just a sequence. And so hopefully you can figure out what that sequence is and then find its limit by using some kind of sequence tricks that we've already talked about. And this is how you can calculate the value of the series. And I will just say this, because that series on the left-hand side is defined in terms of a limit, this lim may not exist. And so I don't think this is a big surprise, but when I look at a series in general, this generally may not converge, right? because it's defined in terms of a sequence. So sometimes that sequence may not converge, and so that means sometimes the series may not converge. So if I ask you to find the value, the answer of a series, sometimes the answer does not exist. All right. Let's try some easy examples, and then we'll do some more interesting ones if we can handle it. So I got 2 easy examples. This is about as easy as it could possibly be. What about a sequence which is just a constant every time? So the sequence I'm referring to is 1, 1, 1, 1, etc. All right? Can we try to evaluate the series? So what is the sum n equals 1 to infinity an? Can we find the answer? Or say the series does not exist? All right? So what this means is you start with these numbers, and I'm going to add them all up. Anyone have an idea? Does this actually add up to something, or does it fail to exist?
It doesn't exist because it's just 1 plus 1 plus 1 forever.
Yeah, ask your kid brother on the playground. What happens if you add 1 plus 1 plus 1 forever? The answer is not like, oh yeah, you get 23 or something. No, it doesn't add up to anything in particular. So I expect the value of this will be it diverges or it doesn't exist. Or you could say, as they say on the playground, you get infinity. This is not, I object on the playground to people using infinity casually like that. But yeah, we should expect the series will not converge, because if you add 1 to itself forever, you don't actually add up to something. But if I want to be very particular about this, we have to, in order to make sense of these, we have to write out the partial sums. And so this is S1 would be 1, S2 would be 1 plus 1, S3 would be 1 plus 1 plus 1, right? These are the partial sums. You add only a few of the terms at the beginning. And now we have to try and figure out, like, can you deduce a pattern of these? So I should actually, we can just straight up add this up, right? That's 2, that's 3. S4 is 1 plus 1 plus 1 plus 1. What is that? 4, yeah. Can you see the pattern? I think you can. Generally, I would like to write a little formula here. Sn equals, what do you think? N, yeah. I hope you see the pattern, right? S2 was 2, S3 is 3, S4 is 4. In general, Sn is n, all right? So calculating the series typically involves figuring out some kind of pattern for the partial sums. So I know that this is the sequence of partial sums, and then I can find the series by taking the limit of this sequence. All right, so Sn equals n, and then this is the definition of what the series means. It is equal to the lim n goes to infinity of Sn. Sn equals n, so this is the lim n goes to infinity of n, and I say that limit does not exist, because it don't, right? This does not exist. Although the more typical language, if you're talking about a series, we say the series diverges. All right, the series diverges. You could say the series diverges to infinity. I would know what you mean by that. It's because the lim n goes to infinity of n, that limit equals infinity. All right, this was a simple example. Any questions about that? You have to figure out what is the sequence of partial sums first, and then you take the limit of that sequence. In this case, no problem. Let's try one that's a little more interesting. This is also a sort of an easy example, but actually there's something interesting about this one, in my opinion. How about the sum minus 1 to the n equals 1 to infinity? This may be something, I don't know, do the kids on the playground talk about this these days? Depends on what kids you're talking to. If you think about what does that represent? It represents adding together forever This, if I were to write it out, would be the first thing is a minus 1, but the next one is a plus 1, and then a minus 1, and then a plus 1, and then a minus 1. It's that. That's what this series represents. Because the minus 1 to the n just represents an alternating sign, -1, and then plus 1, and then minus 1, and then plus 1. And you add them all up. Anyone have a prediction about this? Did you ever talk about this on the playground?
Does it converge to 0?
Yeah, is that 0? Because you get minus 1 and plus 1, and then minus 1 and plus 1? Any feelings about that? Feels like maybe 0 to me. Yeah?
Could it also equal -1? Like
My reaction is no, it can't be 0 and also -1. But why would you say that?
like
This is not a bad.
like if you take the first term and forget all the others, then it's just negative. So then if you did that every
Yeah,
other
yeah.
term
Right.
forever.
So I think this is what she's saying. I would say it in a slightly different way. What if I look at only this part of it? What would you say that adds up to? If you say 0, then something is weird, because if you think this part adds up to 0, then that means the whole thing adds up to -1, right? But you just told me a few moments ago you thought the whole thing adds up to 0. There's something very strange about this, right?
Doesn't it depend if infinity is odd or even?
This is a good idea. Depends if infinity is odd or even. Yeah, is infinity odd or even?
Well, wouldn't it just not exist?
The answer is no. Infinity is not odd or even. Yeah. So because of all these weird eventualities, it turns out this limit does not exist. There are reasons, like I agree on a certain intuitive level, you feel like this should be 0, but actually there are reasons why if you think this really is 0, then it means some other weird things happen. So the only really truly consistent answer here is to say that the limit does not exist. But anyway, we can calculate this using the sequence of partial sums. So let's try and write them all down, right? I will go S1. S1 is just the first number by itself. That's -1. S2 is just the first 2. That would be -1 plus 1, which is 0. S3 is the first 3 of them, okay? -1 plus 1 minus 1. This is -1, right? S4 would be adding together the first 4 of them. -1 plus 1 minus 1 plus 1. That adds up to 0, etc. Can we see the pattern here? I think you can see the pattern here. It just goes -1, 0, -1, 0. Now it's hard to write that as a formula, but I will just say Sn equals -1 when n is odd and 0 when n is even, right? There's no real cuter way to write this as a little formula, but it's clear enough that that's what the pattern is. You know, you could draw a graph of this sequence if you like. It looks like -1, 0, -1, 0, -1, 0, etc. Right? That's what this is the sequence, not an, but this is the sequence Sn of the partial sums. Okay, anyway, what is the value of the series? So, sum -1 to the n equals 1 to infinity. This equals the limit of the partial sums, Sn. And what is that? Sn is the sequence. I drew a picture of it. Can anyone say what's this limit? What does it converge to? Or maybe it doesn't converge. I would say it does not converge. This is an oscillating sequence, flip-flopping between 2 values. That means it does not converge to either one. So this diverges, right? This one doesn't go to infinity. It just oscillates back and forth between 2 values. But in any case, it does not converge to any particular value. Strange but true. This is a slightly weird example, kind of interesting in my opinion. If you keep on adding 1 and then subtracting 1 and then adding 1 and then subtracting 1. All right. Great. We got about 15 minutes. I think this will be enough time to talk about one of our extra important examples is the geometric series. the geometric series. Last time we talked about the geometric sequence. I hope you recall. Last time, the geometric sequence is just, an equals r to the power n. And we talked last time about, depending on what the r is, this either converges or diverges. And there was kind of a theorem that we wrote down in 4 parts, which I hope you remember. If the r is greater than 1, it diverges. If the r equals 1, it converges to 1. If the r is between 0 and 1, it converges to 0. If the r equals 0, it converges to 0. And if the r is less than 0, it diverges. You don't necessarily have to have that memorized so that you can rattle it off really fast, but you should remember all of those things eventually. Anyway, that's the geometric sequence. I would like to talk about the geometric series, which is what you get when you add those things together, all of them. All right, so the geometric series is that same thing but in a series. And there's a weird technicality here, which to be honest, I don't really like, but it's because the geometric series is this. The sum n equals infinity, r to the n minus 1. I don't really like this minus 1 here, but it's because they want to begin, when you write out the terms here, they want to begin with r to the power 0, which is 1. So this, if you write the terms out, looks like 1 plus r squared plus r cubed, etc. And they have to put that n minus 1 here rather than just n. Wouldn't it be nice if it was just the sum of r to the n? It's because you want to include this 1 so that there are going to be some formulas involving this series, and the formulas work out nicer if you include this 1 here. So there's a minus 1 in there, unfortunately. All right, this is the geometric series, and what I would like to talk about is, what can you say about when this converges? So for which r does that converge? And this is a different question from asking when the sequence converges, right? For which r does this converge? And furthermore, what does it converge to? All right? This is what we want to talk about. The sequence itself can only either converge to 0 or 1, depending on what r is, or it can diverge. The series actually turns out can converge to any number, and there are formulas involved in this business. All right? So let's see if we can calculate the series. I think we have enough time to come up with the formula for the value of the series. So if I were to analyze this, I would start by writing the partial sums. N equal 1 to infinity, r to the n minus 1. I'm ending up writing the same thing I just wrote again. Sorry. The partial sums look like, S1 is just 1. S2 would be 1 plus r, right? S3 would be 1 plus r squared. And so on. Can anyone say what Sn would be 1 plus r squared plus blah, 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 plus eventually what will be at the end here? It's r to the, it's not quite n. If you look at these other ones, there's a pattern. Here for S3, I go up to r to the 2. So what is this going to be? Yeah, it's n minus 1, 1 less than n, like that, all right? And can we calculate what that approaches as n goes to infinity? This involves a very weird trick, which you don't have to remember how to do this weird trick because we're only going to do it just this once. In here, I'm going to multiply both sides by r. And check it out, what happens. On the left, it now says RSN. And on the right, well, I'll write this, R, and then times all this business. If you distribute the R, this says RSN equals r plus r squared. It's just all these powers increased by 1. When you distribute r like that. Right? Mm-hmm. And then, check it out. This is the weird step. These are all somewhat weird. I'm going to take those two boxes and subtract them from one another. So subtract the boxes. So on the left side of the equal sign, it'll say Sn minus Rsn, right? I am subtracting the boxes. Subtract the boxes. On the left, it says Sn minus Rsn, and on the right, actually, we have these big sums, but almost everything cancels out because they're like I have r and r. Those are going to cancel. R squared and r squared are going to cancel. Can anybody say after canceling everything, what remains? So not everything cancels, but some stuff doesn't cancel. The 1 remains, right? I have a 1 at the beginning, which is never canceled by a 1 here. So 1. And there's one other thing that never cancels. When we subtract, yeah? R to the n, right. All of these guys, the r and the r, oops, they cancel the r squareds. Here I have rn minus 1 cancels the r to the n minus 1, which I didn't write here, but nothing cancels r to the n. So I end up with minus r to the n, right? It's minus because it never canceled and it's part of the one which was being subtracted. All right, but check it out. Now we can solve for Sn. This is the weird trick. Factor here. And then we can write Sn is 1 minus r to the n over 1 minus r. And we now have a formula for the partial sums. Isn't that cute? This is a weird trick, which, like I said, we're only going to do it this once. This is not a typical thing that you have to do in examples. But it's such an important example of the geometric series that this is worth it for this particular one. All right, now I will just say this is a true formula. I would say when r is not 1, right? Of course, that formula right there is bogus. If r happened to equal 1, then you're not allowed to do that step. But all of the other values of r will obey this formula, all right? And so that means we can now try to calculate this series, right? I started with r to the n minus 1, and I determined that this, well, by the definition of a series, this is equal to the limit of the partial sums, which is, according to that formula right there, this, right? We figured out that Sn equals that fraction. And now, what happens when you take the limit here? Well, first of all, the answer is really all you need to focus on is right there. Like everything else is a constant in terms of n. Really, you should be looking just right here. What do you get when n goes to infinity? This, in fact, if you like, you can use our limit rules to write it this way. Push the lim all the way inside like that. This is because a limit can always be split apart a fraction and also inside things which are being added together. And what is this limit? Well, this is that big theorem that I just rattled off. If r happens to be more than 1, this diverges. If r equals 1, it converges to 1. If r is less than 1, it converges to 0, and all that stuff. All right. So this actually, we already know how to do this. We know this from last time, right? Because it is the limit as n goes to infinity of r. If you care about, if all we care about really is does it converge or diverge typically, remember, the rule is lim n goes to infinity, r to the n, converges, can I say, to 1 when r equals 1, converges to 0 when r is between 0 and 1, like that. This was the rule that we came up with last time, and diverges otherwise. All right? And so we can put all of this together What it means is when I actually do this limit, that part right there, the only thing it could possibly be is either 0 or 1. That's because those are the only values this could converge to. And we can just say what happens in either case. I'm going to write this as a theorem. The proof of it is just everything that we've talked about so far. So it says if R sorry, what I said before, this is what I mean is about absolute values here. I'm sorry, I'm being a little fast and loose here. It's 0 when the absolute value of R is between 0 and 1. Sorry. Even for our negative values, I had misremembered part of the theorem from last time. Even if R is negative, as long as it's between 0 and 1, this thing will still converge to 0. So what this says is if the absolute value of R is less than 1, actually, if you're talking about absolute values, it's not really necessary to write this part. Of course, the absolute value of any number is always bigger than 0, so really all that you need to say is this. If the absolute value of R is less than 1, that means this part here converges to 0. And so that means the series, the actual value of the series, R to the n minus 1, that's the series I'm talking about, equals 1 over 1 minus R. It's that thing which you see at the top there, but using 0 for the limit. If the R in absolute value is less than 1, that limit up top there is 0, and so what you get is this. And if the R in absolute value is more than 1, the whole thing diverges and you don't get anything. So if the absolute value of R is greater than 1, actually greater or equal, then this sum R to the n minus 1 diverges. This is the full theorem about values of the geometric series. All right. So, for example, can we just do one very quick example? So, what if I wanted to do something like 1 plus a half plus a fourth plus a 8? This is that same one I talked about at the very beginning, where at that time I was only talking about this part of it without the 1 at the beginning. That adds up to 1 if you stack them inside that little cute little picture. This I expect the answer to be 2 then, since I'm adding an extra 1 at the beginning. But this is actually very easy to calculate. This is the same as this geometric series with a 1/2 to the n minus 1, right? This formula, adding up powers, it is powers of 1/2. So this fits exactly the format that we're talking about here. It is a geometric series, and so the answer is just given by this formula right here. So that means the sum 1/2 n minus 1 from n equals 1 to infinity, according to the formula, must be 1 over 1 minus a half. And what is that? 1 over a half, which is 2. That's what I said it should be, all right? So drawing the cute little box is not necessary. You can actually calculate that same result using this formula, which is a much better approach than drawing a cute little box, all right? We will do many more examples with this next time. So I'll see you all on Friday. Please let me know if you got homework questions. I'm happy to talk about them.